Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution, and in particular, we're going to concentrate on the concept of how stars form, and we'll walk through the process that goes from interstellar cloud ultimately to the endpoint of a normal star. So let's go ahead and get started. In our galaxy, there are many places where stars are forming, and we talked about that in the previous video. But let's pretend that we're going to watch the formation process of one particular star that comes from a very, very big cloud that might be making thousands of stars as we speak. The one thing we've learned about the stars is they don't form one at a time. They actually form in big batches of stars, dozens, if not hundreds of stars simultaneously. So let's imagine that this is an interstellar cloud, and let's say that right on the corner, right up here, is a place that's very cold and isolated from the outside universe. And if you remember from the previous video, star formation requires very cold temperatures to get us going, to get things started. And here's where we're going to go into a little bit of Photoshop here. Let's pretend that this material is all of this. So that little corner of this cloud is now this set of material. This is a cloud of gas, mostly hydrogen, a little bit of helium, and some dust mixed in as well. Now what I want you to notice is the cloud is clumpy. And I know there's many ways we can say that more scientifically. We could say it's non-homogeneous, but in just reality, it's a clumpy cloud. And the reason why the cloud is clumpy is because in our universe, it's actually very difficult to make things mix perfectly so that things are evenly spread out or evenly dispersed. And so just by the very nature of this cloud, there are places where there's more material and there are places where there's less. So this is a pocket of more material, this is a pocket of less material, this is a pocket of more material, etc. Now, gravity is going to be most efficient where there is most material. Gravity depends on mass. So inside of these very dense pockets of gas and dust, gravity is more powerful. And places in between where there's less material, gravity of the material is going to be weaker. So as time goes by, as we just simply let gravity do its job over a period of time, what's going to happen is this cloud is going to separate into fragments. And so each of these dense portions of the cloud will collapse under their own gravity, and you'll notice the cloud separates or pulls apart into individual fragments. These are still clouds, but it is more of a fragmented cloud as opposed to one big clumpy cloud. Now, each of these pockets, these fragments, are going to form stars. And you'll notice that this also shows us that stars form together in groups. You don't have one at a time. You get batches of dozens of stars forming simultaneously. This also serves the purpose of explaining why binary stars are so common in our universe. If you remember from a previous section of the semester, we talked about how binary stars are the most common situation you'll have in the universe. There are many more binary stars than individual single stars. And this sort of explains why. Because if stars are formed in groups or batches, then you're going to get the opportunity to have binary stars to be more common than single stars. So let's chronicle the events of one fragment. To give you a sense of scale, this cloud, mostly hydrogen and helium and some dust mixed into it, this cloud is about 3 times bigger than our current solar system is today. So about 3 times larger than the furthest planets in our solar system. So quite a big cloud. And this cloud is going to collapse and shrink as time goes by. Gravity is going to shrink the cloud and make the cloud smaller. Now, it's at this point that we have to introduce a little bit of physics to make all of this make sense. And maybe you've heard some of this before, but let me remind you of the 2 main physical ideas that are important. The first one is that in our universe, there's a rule that determines the connection between the temperature of a cloud, the volume of the cloud, and the density of the cloud. And the rule is that when you have a cloud of atoms, if you shrink the cloud and compress the cloud into a smaller volume, the temperature of the cloud has to go up. So a shrinking cloud of gas is going to become hotter and hotter as it shrinks smaller and smaller. The second rule has to do with the rotation of the cloud. And in our galaxy, these clouds that are all throughout the galaxy, they all have some movement to them. And just their natural movement through the galaxy is going to make it so that these clouds have sort of a gentle rotation. Just as they move, they slightly spin. This is very normal. But in physics, there's a rule that says if you have something spin and simultaneously shrink, when it spins and shrinks at the same time, it has to spin faster as it shrinks smaller. So a rotating body that spins and shrinks simultaneously will spin faster as it shrinks smaller. And there's a fancy name for this. This is called the conservation of angular momentum. This is exactly the same physics that makes a figure skater spin faster when they pull their arms in and then spin slower as they pull their arms out. It's just the physics of a rotating, shrinking body. Now let's get back to our picture. The reason why this is important is because inside of this cloud, we have gravity constantly shrinking the cloud, pulling the atoms closer and closer together. So as this cloud shrinks, it gets more crowded at the middle, and of course the rule is a shrinking cloud of gas has to become hotter as it shrinks. So this cloud is going to steadily get hotter and hotter at the center of the cloud. And as the cloud continues to shrink, let's kind of just zoom in on that. As the cloud shrinks, it gets continually hotter. The second thing is as this rotating cloud shrinks smaller, conservation of angular momentum says that this cloud is going to spin faster and faster as it shrinks smaller. The consequences of spinning faster while the cloud is shrinking is that the material of the cloud starts to experience the forces of rotation, and the rotational forces are going to make this roughly spherical cloud turn into a disk. So this round cloud that is shrinking is going to become a disk of gas and dust. And it's a fairly thick one. It's like a donut, if you will. It's not so thin like a pizza, more like a donut. I know the food analogies are making all of us hungry. But it is a thick material, a thick thickness to the disk, and of course it's mostly gas and dust. Now the reason why this is important is this rotating gas cloud in the form of a disk is going to mean that the forces are going to segregate the material at the center from the outer disk. And so what happens is all of the material in the disk continues to move around and around and around, and at the center of the cloud, gravity is continually shrinking the material, making it smaller and hotter. And all of the material in the disk is going to now be permanently separated from the material at the middle. And the material in the cloud, again, mostly gas and dust, is going to stay separated into this disk, and the very center of the cloud is going to continue to collapse under the force of gravity. Now, if enough time goes by, this continues, the cloud gets more hot at the middle, the material in the disk continues to go around and around, and after a sufficient period of time, we end up with a main sequence, or a normal star at the center, surrounded by a system of planets. Because inside of the disk, all of the forces that are involved with the material in the disk is going to steadily pull that material together to turn it into planets. So it is now believed that when you form stars, that you for the most part have to form a series of planets to go with the star. And what I would like to do is show you a video. It's only about a minute long, but it's going to take all of these individual steps that we just talked about and put it all together in this one sort of a conclusive video to bring in these ideas together. So let's have a peek at that. So this is, and let me start the video here, this is a cloud of gas and dust, and you'll notice it has a rotation to it. And the forces of the rotation, as well as the force of gravity, combine to make the cloud begin to flatten out into a disk. Because the cloud is shrinking and getting smaller, it's getting steadily hotter at the center of the cloud. And as the cloud flattens out into a disk, you'll notice the material in the disk is now moving around in a way that keeps it separated from the interior. So all of this material in the disk is now segregated from the center of the disk. At the center, gravity is very powerful, and it's slowly shrinking the material, making it hotter and hotter, turning it into what is ultimately going to be a star. The material in the disk, however, is also going to start to coalesce and come together, and it starts to create the planets that will someday orbit around this star. And when it comes to the sun, this entire formation process took somewhere in the neighborhood of about 50 million years. So think about it as 50 million years from cloud, eventually to main sequence star, with a family of planets that go around it. Now, the reason why this is critical is there's evidence of this even still today. In our solar system, all of the planets go around the sun in the exact same direction. So all of the big bodies, the planets in our solar system, go around as if they're still in this disk. And the sun's rotation on its axis is also in the direction of how the planets move. So the spinning sun and the orbiting planets have movements that are left over from this formation process. So we can confirm that this is exactly what has happened, and we still see the evidence of that 4.5 billion years later, even to this day. So in our galaxy, stars, when they form, they are going to make the star at the center surrounded by planets. And this is part of the reason why we have discovered so many planets going around other stars. It seems to confirm that this is actually happening. What I'd like to do is show you some pictures of places in our galaxy where we can actually, at this very moment, see this process occurring. And let's look at a couple of examples here. Let's go back to the constellation of Orion, and if we were to take a telescope and if we were to look specifically at this part of the constellation, you'll notice this sort of a fuzzy cloud right there has the little hint of the pink color. So we're going to zoom into that. And this photograph here, the box that is this photograph is the box that is outlined right here. This star right here at the top left is the star right up here, and the fuzzy cloud down here at the bottom center is this part right here. You'll notice the color. This is hydrogen gas, and in particular the part of Orion that looks like the sword hanging from his belt. This is called the Orion Nebula, and what we're going to do is we're going to zoom into just that part right there. So this is the Orion Nebula. Notice the traditional pink color of hydrogen gas, lots and lots of dust mixed in. But at the very center of the Orion Nebula, there's a cluster of stars. Let me reveal those. And the cluster of stars are the young stars that have formed inside of the cloud that is the Orion Nebula. This is a Hubble Space Telescope image. The colors are artificial. In reality, the colors are actually more pink, but this is what's called a false color image. And you can actually see the individual stars inside of the Orion Nebula. What I'm going to do is switch to an infrared image, because when we switch to infrared wavelengths, all of the gas and dust goes away, and we reveal the stars. So these are the many, many, many stars that are forming inside of this giant star-forming cloud. So you can actually verify that stars form in big groups, many, many of them forming at the same time. And these are the young stars that are in the process of forming that will be future generations of stars coming from this cloud. So this is a stellar nursery where these stars aren't quite finished forming, not just yet. Now, we're going to zoom in a little bit closer. So this is still the Orion Nebula. And the Hubble Space Telescope took some pictures that were really quite revealing. In particular, there was this one portion of the Orion Nebula that had some interesting looking objects. And so some astronomers decided to examine that portion of the cloud with greater detail, and that's what this box is here. You'll notice the weird shaped cloud. There's a couple of them, and you'll notice the very dark one right here. So these were scrutinized, and what the astronomers realized is that these little dark shaped clouds are clouds of star formation. You can actually see the bright center to this cloud. That is the young star, not quite finished. We call these protostars, surrounded by a disk of material. And these disks of material will ultimately be the stars, planets. In other words, it's family of planets that go around the star that is in the process of forming. So we actually have places in our galaxy where we can confirm that all of the physics of star formation is truly as we expect, and that we do actually get the material that will be planets surrounding these stars. In the next video, we're going to talk about how do stars produce their energy, and we'll see the fascinating way that our sun turns its material into the light that we see. I hope you'll join me.